about eliminating those problems and ensuring that it continues to function properly for the life cycle of the building. That's the only way we're really going to get the return on investment from an energy project, is to ensure that it continues to function properly. And of course, we have to provide a safe environment as well. So many factors can influence containment. Let's verify that we have in fact seen the slides.
See the slides?
Okay, great. All right, so these factors we've talked about: the work practices, the hood design and configuration, the lab supply. We've talked about the issues of the controls and the exhaust stack discharge and the potential for it to be re-entrained. All of these factors can influence the ability to protect the occupants, as well as the ability to maintain energy efficiency. So if we're looking at these issues over time, we've evaluated that our understanding of the risk and some of these factors have led to the development of more safer technologies. And so the fume hoods are getting better designed with the high performance hood components. The variable air volume controls have been improved. We're now implementing demand control ventilation and occupancy sensing to allow the management of the systems and reporting of information so that we can control when and where is the air supplied. And we have better means to distribute the air in the space. And these are all developments that have occurred because of the testing. The testing has identified some suboptimal conditions and allowed for the development of more advanced controls and components. So let's look into the system a little bit and look at the management of this information for a building. Well, one of the first questions we have is what kind of information is available. We always start with a review of documentation. When we want to know whether there are master building documents, you have current mechanical system diagrams, what are the airflow sequences of control, do we have an airflow spreadsheet showing the operational specifications, and when was the last commissioning done, or a building health and safety report that shows the condition of the operation of these spaces. Ideally, we would like to have some diagrams that show us the breakdown of supply and exhaust. And why drawings are not color-coded, I don't know, but it seems easy enough to do. And so to be able to identify air supply and exhaust ducts will help us better manage the system. So it needs to be easy to identify. Now, one of the things that we were tasked with doing by the Department of Energy, and specifically the National Renewable Energy Lab, a fellow named Otto Van Geet, is he said, Tom, it would be helpful if we had a roadmap and we could define what these conditions were and the types of information that we need. And so an airflow management program is basically the user's manual for a building, and it would have the drawings and the line diagrams for the systems, the risk matrices showing us where's the risk, the flow specifications, our key operational metrics in terms of maximum minimum flow, the sequences of controls, our standard operating procedures for testing, training of all the building staff and stakeholders, and finally a management of change procedure. And this would define the airflow management program for a building, similar to a car that has a user's manual, oftentimes found in the glove box of the car. Maybe you maybe have or have not looked at that document, but a building should have that similar type of manual. So if we look at a building and we said, okay, what's happening from the air supply and exhaust standpoint, we could use the tools that are available today to do some geospatial engineering and identify parts and pieces of the systems. And we can use this information to identify where the air handlers and the exhaust fans. And from that, we could create a diagram that shows us that roof level and then identify the specific air handlers and exhaust fans and what units or areas that they serve. So if we had a unit, we said, well, this unit is RSB 15, we could come over here and see exactly what type of area that this unit serves, so that if there's a problem with the unit, we could see the impacted areas, or if we have the areas with an issue, maybe we could go back and identify the unit more readily. Peeling that layer away and looking at the floor diagram, we might be able to then locate where are the areas served, so we can color code the spaces. So we know that this unit 15 serves an area of lab spaces So again, being able to more readily identify problems and then go directly to that source. A line diagram can actually help us match the unit to the valves and the areas served. So if we took a unit here, this EHEAU 8, and we looked at the branch ducts and all of the areas served, we could then identify what would happen to these spaces if we had a problem with that unit, or we had to shut down the unit for some type of activity, or if there was a problem with some of the spaces or some of the valves. This is able to identify what unit serves those spaces. So we recommend that this be included in the deliverables for all commissioning projects, that you get these line diagrams, and then you can use that to better manage the systems. Now, taking the next layer is the floor plan and showing where's the risk, right? We know that labs aren't one size fits all. In this particular floor plan, we see on the perimeter, we've got offices, and then we've got support spaces, and all down the center are our laboratories. And each laboratory appears to be the same size and configuration. So you might assume that they're doing the same level of work in each space, but that's not true. There may be different activities within those spaces, and we have to identify where and to what level is the ventilation required, and are additional safety measures required, and where is it critical that we have the appropriate flow. So we have to have a tool that allows us to evaluate this space, and that's our risk assessment. So working with the University of California, Irvine during the development of the Smart Labs program, they said we need a means to evaluate the risk associated with the hoods and the laboratory so that we can use that to derive the required operational specifications. So this information was developed, this approach, and all the tools are available on the Department of Energy, the I2SL Smart Labs website. I'll show you that address. But essentially, it's a process that you go by and evaluate the laboratories and look at what's the risk associated with the activities. Each hood and each laboratory is going to be rated based on a scale of 0 to 4. And the risk factors are going to allow us to identify areas that may have lower or greater risk associated with the activities. And each area is then associated with an emission scenario that's commensurate with that level of risk. So a level 0 may be using small quantities of negligible hazards, and we're not all that concerned about an inhalation hazard. Whereas a level 4, maybe they're working with a much higher level of toxicity, greater quantities, they're generating the materials in different ways, and we have to have a much greater level of attention to the operation of the ventilation systems. So we evaluate risk factors, looking at each hood, looking into the hoods, and identifying what type of activities are being performed. We want to identify the types of hazards, whether they're chemical, biological, radiological, how are they being generated, the quantity of materials, the potential for them to become airborne, how the generation locations, the housekeeping, and the dynamic nature of the work. Clearly, there's a difference in these two hoods. The one at the top is using small quantities of low hazards and not adding a whole lot of energy. The one at the bottom is a much different application of hood. They're making and synthesizing new materials. They're adding energy to the process. A lot of these materials could be very hazardous. So these hoods may have different operational requirements in order to protect the operators. So if we were to do an energy project and wanted to reduce flow or reduce face velocity or minimum flow, we'd have to be very careful about which hood we were applying those techniques. So a scorecarding approach, by scorecarding these risk factors, we can take hoods through the spectrum of a hood that's not in use as it begins to increase in its risk level, to a hood that's adding a lot of energy to the process or creating new materials and doing a lot of stuff where airflow becomes very, very critical, are going to end up with a higher score, and that gives us the ability to segment these hoods. And then putting them into a list, we can take the list of hoods, look at the different risk factors and the ratings, and then identify those areas that have a higher risk profile, and then look at the distribution. And we find in this case that a large percentage of the hoods are in the 0 or 1 category, we could consider hibernating some of those hoods or taking them out of service or possibly operating them at a lower flow. But we also have a significant number of hoods in the 3s and 4s, which says that we have to pay very close attention to those hoods. From that, we can start applying different operational specifications, different face velocities, minimum flows, duct velocities. These are all a function of risk. So each hood by its rating allows us to evaluate. Now you might take a rating and say all hoods are going to operate to level 3 or all hoods are going to operate to level 4, but that may make it easier to manage, but maybe we're giving up a little bit of flexibility and energy savings. So it's all up to the facilities to determine how to appropriately apply these techniques. We want to look at the risk associated with the hood because it may change. Now in this case, it says it was washed by RSF, but what does that mean? When we look behind the baffle and so forth, we see still a lot of residue, and this could potentially still be a fairly hazardous hood. This just came in today. One of my guys sent me a picture, and it says on here, it says, this unit is not to be used at all for ventilation, storage, or experiments. So I don't know what you make of this hood, but certainly what is the hood doing at this point other than maybe holding the work surface down? But it's certainly not being used or appropriate for a laboratory. So risk can change. We need to keep track of it. Now, applying the same concept to a laboratory, if we walk into a laboratory environment and we use our scorecarding approach with these risk factors, we can take a lab that really has nothing in the way of inhalation hazards. We're not as concerned about the air change rates or about the velocity profiles in this type of space. But as we move down this spectrum of risk and we get to a more extreme environment, now with many different types of chemicals and materials, it becomes very critical that the ventilation systems operate properly. And this is a picture of me in the nuclear non-proliferation lab, and I can tell you it's a pretty interesting and hazardous environment. So each lab now can have a score, and that score allows us to then segment those spaces by risk. And so each one now has a transferable score that gives us an ability to look back and say, what was it being used for? How do we apply that score? And in this case, we have 60% or 70% of our labs in the 0 and 1 category, and only 2% out here in the category 4. So that gives us some opportunities when we begin looking at now our floor plan color-coded, and enables us to identify these areas of high concern. And this is important because not only are we going to apply operational specifications based on this segmentation, but from a testing and a maintenance standpoint, it tells us where we really need to be concerned and take special precautions. The distribution may vary in buildings. We have some buildings that are chemistry buildings. You expect them to be a higher range of risk. And other buildings, maybe they're in biology or they're doing electronic type of research where they're at the lower end of the spectrum. So each of these spaces then can be associated with a operational requirement based on risk. And so a category 0 through 4, as we move to the 4 categories, it's more critical that we have the appropriate amount of ventilation, that the isolation is being maintained, and that it also allows us to define other factors around the ability to use energy recovery, emergency purges, and other types of factors associated with design. So segmentation goes to speak about the lab ventilation design level and how would we make the appropriate specifications so that when we test it, we know what we're actually looking for in our expectations. Now, all of these flows for the hoods and the lab should be defined in a flow matrix or what we call a flow spreadsheet. And when we look at the flow spreadsheet, we have a list of every lab, we have the size, we have the risk control band, we have the air supply, the transfer air, and the min-max flow for every hood, and the calculated air changes. This makes it very simple to confirm that the controls are properly set up and that we have the expectations of flow in each individual space. And if we set up this flow spreadsheet correctly, we can use it to simply add up the flow to determine our min and max flow for the fans. So if we wanted to see how much flow was required at minimum or maximum, we use the flow spreadsheet to quickly add those up. our flow spreadsheet is connected to the line diagrams so that we have a way of managing the systems going forward. So now we take this theoretical information and we convert it to the actual. And we have an expectation that this system is going to modulate flow. It's going to go from some high to some low flow. And based on the summation of these valves, we're going to get that range of flow. But how do we know it's working properly? So we need to compare the theoretical to the measured and the reported, right? So if we have an expectation that flow is going from 250 to 1,000 CFM for the hood, that's our theoretical. But now we have to test it through our hood testing methods that we've covered yesterday and today. We can then confirm that we're getting that 250 to 1,000 and then compare that to what is the building automation system reporting. And I can tell you there's oftentimes a very significant difference between these three values. And if you don't calibrate them correctly, if you can't measure it properly, you can't control it properly. So this strategy of looking at theoretical, tracking it, comparing it to actual measured, and then using the building automation system to report the values. So how do we keep it all working? This sounds very complicated, right? And it is. It's complicated because a lot of systems are installing these more complex systems, but they're not improving their management and maintenance techniques to take advantage of the systems and keep them working. So what we'd like to think about is a top-down approach. A lot of times fume hoods get tested on an annual basis, and you get those fume hood test reports back and you say, oh, there was a failure. Well, why did this hood fail? Well, it was the control valve or it was the fan. And after doing this for multiple years, we determined that we're doing it in the wrong way. We really need to start at the top. There's no reason to test the hoods until we know that the fans are working. And if the air handlers and exhaust fans aren't working, why go and do a lab hood test, right? We're just going to fail it and then have to repeat that test later. So what we've done now is started with a top-down approach. A group goes through and checks the air handlers and exhaust fans first. They're then working properly. Then we check the controls to make sure they're modulating flow, and then we challenge the hoods and the lab environment to make sure that they're functioning to meet the needs of the occupants. And so by looking at this top-down system tests, lab environment, and fume hood tests, you'll alleviate a lot of problems and keep the systems working properly for the life cycle of the building. So putting this in kind of a flow chart, we start with a group that goes in and does the air handler and exhaust fan PMs first. Then when that activity is done, it moves to the controls group to modulate the flow for the different valves. And then making sure that they're functioning, then we go to the lab environment and the fume hood tests. And then once those are working properly, we know that the building automation system is providing good information, good data, and we can use that to monitor and trend. So this process is sequential. Mechanical equipment first, then our controls, then our lab environment, our fume hood tests, and ongoing monitoring. So it's sequential. And if you take this process and then work it over a series of buildings, this happens to be the EPA and Research Triangle Park, that group of air handler exhaust fans moves from one building to the next. And they just cascade through the course of the year to make sure that all of those units have been maintained and are operating properly. And right behind it, a management coordinator comes in and says, all right, controls group, go and challenge the VAV controls and the operation of the sensors and actuators, and do that in each of the buildings. And right behind that comes the lab environment and the hood tests. So all of those activities are sequenced so that the building is operating properly, and you can minimize resource time and expense by up to 30% just by coordinating the work, and then eliminates all kinds of duplicative effort of having to test, diagnose, fix, retest, diagnose, so forth. It allows you to eliminate variables and get more consistent operation. So improper maintenance repairs can be a factor that really influences a lot of issues. Oftentimes we'll see that, hey, the fan's working, it's been maintained, but nobody checked to see if it's still connected to the main duct. And so we look at this kind of an issue here where the separator between the fan and the duct for vibration isolation is disintegrated. And so we're not pulling the the flow from the hood anymore. It's being bypassed into the fan. So we could get a false sense of safety by saying, yeah, the fan's operating, we're getting the right flow through the fan, but it's not coming through the hoods. So we need to look at it holistically. If we look at a building and we put our hoods in our system, it's the same diagram we've been looking at. Again, where would we start? What areas are really important and where do we have to look at risk? So if we had our risk assignments here and we said that this hood is a 3 and this hood is a 4, this risk control band 4 hood means the valve serving that hood is also a level 4. So whatever hazards are going through this hood are going through that valve, right? So if I'm going to go work on that valve, I better be careful that I'm taking appropriate personal protection because the hood is working with a high degree of hazards that are transferring through that valve. And that's also going through the system. Now, if I come over to this hood, I'm a little bit less concerned about this one, but still have to make sure that we're taking the appropriate measures. If I look at this from a maintenance priority, this valve is very important to the operation of this hood, and this hood is very important to the safety of the occupants. So that may establish our maintenance priorities. And so looking at this kind of a risk assessment, identifying the components of labs, helps simplify the establishment of maintenance priorities, making it easier for us to schedule and prioritize maintenance so that we are concentrating on those areas that have the most importance first, and then using that information to better manage the systems. So I hope that makes sense. Now, all this information we want to pull back into some type of building automation system or an information system that allows us to manage and monitor. So we need to use the different tools and techniques, the key metrics. Key metrics are how much flow are we expecting, right? That should be defined during commissioning and changed whenever there's a modification of the system. We need to make sure that what's the theoretical is actually being is actual, and then it's being reported correctly, and then use this information to report the operational status of the building. So with this operational status, we can tell whether the building is operating as it did when it was commissioned. In order for us to ensure safety and to provide a energy efficient system, we want to be able to monitor, identify when things are operating out of control. And so this information all adds and feeds to this ability to better manage the systems. Looking at the operation of the air handlers and the exhaust fans, the ability to visualize, there's a lot of data on this sheet. How do we confirm that it's accurate? And that's through the testing. Verifying that the flow is as we expect it, and then make sure that's being reported correctly. That's going to save us a lot of time. And then once we have confirmation, we can use this information to establish maintenance procedures and better manage the performance of the systems. So setting up these sheets is kind of an art, but we want to make sure that we have the appropriate information and that it's been challenged. So when we go to the fume hood and we look at the reported values, we're confident that this value is correct and that we understand where or when it might not be operating as we anticipate. One technique that was developed at the General Motors for visualization of performance is we're managing the labs there, and we want to get a quick glance at how things are working. And so just using a high-level information sheet that we look at very quickly and identify everything is working properly. So we can start the day, pull up this sheet, see if there's any operational issues with any of the systems. We can then also dive in a little deeper and take a look at the units themselves and compare. And in these comparisons say, well, if the damper is closed, but we're still meeting set point, that's a check and balance that would give us an indication of a problem. So we can have these checks and balances here that give us the ability to compare automatically and be able to say, well, if this condition was true, that can't be true, and therefore it's a problem. So we can automate some of these tasks and make it very simple for a building operator to identify problems. Again, the information on these sheets can be a little bit overwhelming. You can put so much information on them, and unless you're an expert, you wouldn't be able to just glance at it and tell there's a problem. So information has to be represented properly, and visualization is really key. So in this case, we look at the color coding, we see they're all green, and that tells us very quickly that we've got the appropriate flow and that things are responding properly as we would anticipate. We also have another scheme here that's looking at visualization of fume hood use. So we've got a couple of pictograms here that show us whether the lab or the hood is occupied or unoccupied. If it's red, it's unoccupied. If it's green, it's occupied. We look at the face velocity and the flow of control. If it's green, it's good. If it's red, it's not. And so very quickly we can kind of glance across the hoods and use this to identify any problematic components. And then if we are interested in looking at the occupancy or utilization, how often are these hoods occupied? How often are they leaving the sash open? So this kind of information allows us to now begin calculating the occupancy and then correlating that with operation. If the operation's not matching the change in occupancy, then we've got a real problem. So this allows us to visualize the airflow and allows us to report it. There's many different systems to put this information together. It's really about what works for the individual building and how best to represent that so that it's easier to manage. One of the key elements that's being developed now is the building analytics. The information that comes in, it can be overwhelming from so many different sensors and actuators. How do we extract the information that's important and use it to identify problems and then issue work orders that are appropriate, that really address the issue and don't have to have hours and potentially days or weeks diagnosing problems? Through these advanced analytics, you can look at comparisons as we've demonstrated and use that information to target operational anomalies and then use that information to better manage the system. So lots of tools are being developed, but we can get overwhelmed with information, and we need to really boil it down to a more simple representation that allows us to better manage these systems. Otherwise, we're going to put the health and safety of the occupants at risk, and we're going to risk getting the return on investment from the building systems. So more data is not always better data. We get overwhelmed with the information. There's a ton of information on this sheet about the fume hoods and their valves. But if we look at this information, we start seeing some problems. Now, you are experts out there. You're probably looking at this and already starting to identify some things that they don't look right. All right, we can look at some of these different values, like maybe the air supply. Well, in this case, the supply flow set point is 716, but it's only showing 0. The damper is 7%. How is that possible? Over here, the flow set point is 1584, but the damper's at 46%. The supplier volume's at 0. Something's not adding up here. We can look at another parameter, the room offset volume. The differential set point's 40. Here it's 756. 40 CFM, 1600. Something's not right. It's not working out here. Why isn't this identified and made more aware? And then we look at the hoods. If we look at the different velocities here, it goes from 100 down to 60, which is right. How do we have confidence that the information is reporting is correct? And that's very critical, and it comes through testing. Using the right test methods, applying them appropriately, allows us to have confidence in this information. So hopefully this will help to better manage the operation of the facilities. So again, I can't stress this enough. Without proper testing and maintenance, the controls are going to become dysfunctional, and those dysfunctions may show up in safety issues, may show up in odor migration, pressurization issues. It may show up in inability to achieve the energy objectives, or quite frankly, interfere with the research. And so now, as we're looking at the impact of ventilation on COVID transmission, the importance of ventilation is even more critical. It's not only associated with labs, but any building environment. So maintenance, testing and maintenance is really, really important, and we have to have the appropriate procedures and techniques. So employing this kind of program where we've been involved in implementing a management program, we've seen failure rates reduced. In this extreme example, we were seeing 50+% failures on an annual basis. By understanding the system components, looking at the testing and implementing a good maintenance and management process, we got this failure rate down to less than 5% or so a year. Now that was a major savings in terms of time and resources and so forth, and it gave more confidence to the occupants that they were operating in a safe and productive laboratory. So the LVMP really does help. So these new methods are being employed by lots of different organizations around the world, and so hopefully you'll find this information to be helpful and will help to, you can take it to your facilities or to your customers and implement these tools. And if you ever have any questions, we're happy to help and participate. So at this point, we'll go to some questions. And again, before I start answering the questions, I do want to also express my thanks to everyone's time and patience today. We appreciate you taking the course, and we apologize for some of these technical glitches that occurred today. We've got a little bit of weather, a little bit of internet issues, and some technical difficulties here, but we're overcoming those problems. So hopefully you've still gotten some value out of the material, and it'll help with your end objectives. Okay, so we have a question. How do you determine what the bypass opening should be? That's a great question. So I'm going to see if I can locate that slide here real quick, and we'll go to that information. All right, so our bypass maybe I don't have it readily available here. Here we go. All right, so the bypass opening. All right, when you look at maintaining a velocity through the face, the opening area when the sash is open is the width times the height. And let's say that you're trying to maintain 100 feet per minute and you've got a 10 square foot opening. Well, 100 times 10 is 1,000 CFM. But if you're trying to maintain 100 feet per minute and the minimum flow is 250 CFM, you only need 2.5 square feet of opening. So if we're trying to maintain 100 feet per minute with a flow of 250 CFM, right, we can put 250 CFM divided by 100, and that equals 2.5 square feet. If we know the area under the airfoil, let's say that that's 1 square foot, then the bypass opening has to be 1.5 square feet. So you can take this bypass opening and adjust it till you get 1.5 square feet, plus the 1 square foot gives us 2.5 square feet, and that will equal the 100 feet per minute at 250 CFM. It's all a matter of math. We set the bypass area based on math, and it's just a simple equation that Q equals velocity times area, and the area is equal to the bypass area plus the airfoil sill. So it's just a straight math issue. The bypass area is set based on the flow and the required velocity. Okay, hopefully that helps. Okay, next question. Do you have to adjust for altitude when conducting either operational or performance tests? Okay, altitude is interesting because with altitude becomes density of air. So if you are measuring velocities through the hood, when we measure this velocity, most of the test equipment that we use is calibrated at sea level. And if you go up to Mile High City in Denver, where it's 5,250 feet above sea level, the density of the air is different, and it's going to report differently in terms of the mass flow. It's going to be different at a mile high versus it is at sea level. So yes, we absolutely have to account for altitude in our measurements, but we should be able to identify this by looking at the pressure of the air and accommodate that in the equations to adjust our calculations. Now, it's probably not going to be impacting pressure but it'll impact velocity, right? It may not impact tracer gas containment, but it will impact other factors. So it's important that we look at the testing under the conditions that are found, and under those conditions, ensuring that they're appropriate to achieve our objectives. So correcting for altitude is very important. We have to take that into consideration. So next question is, can the tracer gas test be optional for hood certification? Well, I'll tell you what my opinion on that is. As we learned yesterday, let me go up here. The fume hood is the primary safety device used in laboratories to protect people. When a researcher works in a hood and they're using some unknown materials, some materials that may be immediately dangerous to life and health, right? They expect that fume hood to perform to protect them. And they have a confidence that if they see a sticker on the hood that has been tested, that sticker is suggesting to them that it's working properly, it's been tested. Now, the test itself is insignificant in terms of the cost of installation. A typical ASHRAE 110 tracer gas test can be $250 to $500. But the hood to install is $25,000 to $50,000 to install. So the cost of testing is less than 1% of the installed cost of the hood. So it's only installed to protect people. So in my opinion, during an as manufactured test or an as installed test before people use it, we owe it to the occupants to use this test to ensure that it functions properly. And in fact, the OSHA requires that you take measures to assure proper functioning of the fume hood, and it requires that you use the most recent test methods available. And guess what? That's ASHRAE 110. That's a tracer gas test. So for an initial certification test before people use it, yes, you should do tracer gas tests on every hood. That's my opinion. However, in a subsequent routine test where the hood's been installed, maybe it's operating for a year, if nothing's changed, you go back and it has the same face velocity, the same VAV response, the same cross drafts, the same use of the hood. There's no reason to anticipate that it needs to be tracer gas tested again because it's operating the same way that it did when you tested it. So from a routine test, not required, but from an as installed test, required on every hood. Okay? Okay, next question is, how do you get certified to test fume hoods? Well, that's an interesting question as well. There's no real regulatory requirement to get certified. However, there is a necessary demonstration of competence, and a certification provides that. So you could look to the National Environmental Balancing Bureau. They have a certification for fume hood testing, as well as does the Controlled Environmental Testing Association, CETA, has a test that can be applied to get certified. So I recommend that if you're going to be doing this or undertaking this kind of testing, because people's health and safety rely on these measurements, that it would be good to be certified and make sure that you're using the appropriate methods, the appropriate equipment, and you're analyzing and reporting the data correctly. That's just part of the question. Okay. Now, there's another question here that's about a scenario. Okay, this one's talking about baffle positions. So let me go to a diagram that'll give us a little bit about baffles. It may not be exactly appropriate, but maybe we can use it. Okay, let's forget the airflow visualization ratings and use the baffles as an example. Okay, so the question is, when using a fume hood with an adjustable baffle, open, normal, or closed, meaning you can adjust the slots, the top, middle, the bottom slots. They were originally adjusted based on lighter than air or heavier than air materials. What was influenced was the airflow patterns within the hood and the airflow patterns through the opening. So there is some cases where you can adjust these baffles and it influences the containment capability. When we looked at the impact of baffle position on the hood, we found out that, let me go here. When we looked at this baffle position, top slot, it's flowing towards the top. When we went to the bottom slot, it's flowing toward the bottom, and we're maintaining containment. So it says, when using a fume hood with an adjustable baffle, open, normal, close, for environmental sample extraction, you dilute acid solutions containing nitric, hydrochloric, hydrofluoric that are heated. Heating the acid vapor may be lighter than air, and some acids may be heavier than air or settling. Should the normal baffle position be used? Well, in this particular case, we have materials that are going to be generated and we want them to be captured by the hood. And we want them to remove the materials. So if you have materials that are evolving into the top portion of the hood versus the bottom of the portion of the hood, how would you know the appropriate baffle setting? We now recommend that baffles be set based on containment, not on the process. They should be adjusted so that you get a sweep of air through the hood. And that sweep of air should be coordinated so that it's helping to maximize the extraction of materials. Let me show you this. So if the hood is properly designed and has the appropriate aerodynamic features, the bypass, the flow through the opening, and the baffle settings, it should be helping to sweep the contaminants out of the hood and remove them and dilute them. The baffle should not have to be adjusted for the type of process that's going on. The hood should be designed so that it could equally remove the lighter vapors or the heavier vapors without any adjustments. And that's just an aerodynamic design for the hood. If the process exceeded the capability of the hood to contain, then the fume hood may not be an appropriate device. There may have to be some modifications to the hood or some additional or a different type of an exposure control device to accommodate that process. So that's a really good question, but it's one that requires kind of a depends type of answer. When working with concentrated hydrofluoric acid in the hood, should the baffle be set to open because HF is lighter than air? Again, the lighter than air or heavier than air was just a concept that was used to justify adjustable baffles. Today, we know that that concept's not valid. We should have a baffle that will control the generation regardless of the process in the hood. And if it doesn't, then we have to look and see if that hood's appropriate for that application. And maybe we can make some adjustments from there. But I wouldn't make adjustments based on the process unless I was able to identify that it was in fact the device was not appropriate for that application. Okay, so in summary, we want to make sure that the hood is the right device for the application. We have to look at the risk associated with the application and then utilize the tools effectively. So I'll stop sharing here. I think we're right at time here, and I want to really say thank you very much for your time and your patience. I hope you found value in this course. The slides should be available for download. If not, please let us know and we'll get you a copy of the slides. There will be a recording of this sessions, and you can access that when you receive the, should be in a week or so, you'll receive a link to the video so you can rewatch them again should you have that pain threshold where you'd want to watch this again. But in either case, if you have any questions, feel free to reach out to us. We're always here to help. And again, thank you very much. I hope you remain safe and healthy and have a good day. Thank you very much.